Okay, hello, everyone. I'm Yuxin Deng, so I'm very happy to chair the following session. And we're going to have 3 talks all about, I think, bisimilarity or biosimulation. The first one will be given by Jan Martens, right? About biosimulation by partitioning. Okay, so please, Jan. Hello, Jan Martens.
Oh, sorry, I was expecting that you would start the presentation, the recorded ones.
Yes, I will.
I think it's already, the recording is in progress.
Share screen.
Yeah, we can see your screen. Is there any problem?
I think the format is not accepted because the size of the file is very large.
It's very small. I know.
Yes, so I will share my screen. Then I will put the video.
That's good.
Okay. So it's this one. Do you see the screen now? Is it working?
Yeah.
Okay.
No, I cannot hear a presentation.
No, the sound is not working now.
Oh. Let me start.
Biosimulation by. Hello, thanks for joining this presentation. My name is Jan Martens. I am from the Eindhoven University Technology, and today I will present the work Biosimulation by Partitioning is omega n plus n log n, which is joint work with Jan Frieso-Grote and Erik de Vink. So, biosimulation is used to express behavioral equivalence of concurrent systems. It is a relation on labeled transition systems, and it is widely used to model and check behavior of these systems. A well-known algorithm to decide this strong biosimulation is the Page-Tarjan algorithm. It uses partition refinement, and it has the best known complexity bound for this problem, which is m plus n log n, where m is the number of transitions in the labeled transition system and n is the number of states. So the motivation for this work is the question, can this algorithm be improved? What if we constrict the case to deterministic LTSs with a fixed number of action labels? Can we make an algorithm that decides strong biosimulation faster? And the answer we found is not with partition refinement. So in order to get a better bound than the m plus n log n, we really need to find a new method which does not look like partition refinement. In this presentation we will first discuss what a partition refinement algorithm is. Then we will introduce a labeled transition system which is deterministic, and it's called BK. We call it bisplitter. And it has a growing set of actions. So for each k, if the k is larger, then it gets more action labels. But it has the exact splitting behavior that our result relies on. And in the next step, we will modify this bisplitter BK to obtain the LTS CK. And CK only has a fixed action set, namely 2 action labels, and it's also deterministic. And within this CK, we have that any partition refinement algorithm performs according to a lower bound of this m plus n log n, which is the runtime performance of the page turn algorithm. For the last bit of the presentation, we will also look at a small detour where we look at another approach, which is not captured by partition refinement algorithm, and we rule it out with the help of an oracle. So let's start with partition refinement algorithms. A partition is a cover of the set of states where states are grouped in blocks. So in this example, every state is in the same block, namely block 0. But the initial partition can also consist of multiple blocks, and then an algorithm will refine these partition based on the behavior until a stable partition is found. So in this case, we see that the state S4 and S5 are deadlock states. They have no outgoing transitions, and the state of S1, S2, S3 have outgoing transitions to states which are in block 0. So we say these states reach block 0, and state S4 and S5 do not reach block 0. And this is why we can split this in two blocks containing the state S1 to 3 and one containing S4 and 5. So now we have two states S1 and S2 that reach block B1, but S3 does not reach block B1, and they are in the same block. So this is why we can split block B0 in two blocks that reach block B1 and one that does not reach block B1. And so now we obtain this partitioning. In this partitioning we have one more split left to do, namely S2 is able to reach B2 and S1 is not able to reach B2, hence we can split them and obtain a stable partitioning. So this partitioning is stable and we have no states in the same block that are that we can split. So a theorem tells us that this is now the bisimilarity equivalence class we were looking for. And this is an old observation which is back to in 1983 by Kanalax and Smolka, and it's basically why all these partition refinement algorithms work. So now if we look at the sequence of partitions that this partition refinement algorithm has, it will form a sequence of this kind, where every consecutive partition is a refinement of the previous one, and this symbolizes a run of a partition refinement algorithm. That have this principle where each next state is a new partition which is based on the old partition, and then some blocks that are split. And it's important to know that there are multiple ways to partition a set in order to obtain the stable partition, and we will show that all the possible partition refinement sequences will have the lower bound we suggest. So when we go from one partition to the other partition, we want to know what the minimal cost is of doing this, and what we count is the number of states that we have to move. So for instance, if we want to go from the partition pi1 to pi2, we know that the block 0 has to change in order to become two blocks, where one block has only two states, S1 and S2, and one block has only state S3. And the smallest amount of work we can do is by maintaining the largest block B0, so the one that maintains the most of the states. So we only have to move the smallest part out of the block. So we create a new block for S3, and we move S3 to this new block, which is one atomic action. And this way we count the least amount of work to move the states around. So this is the minimal cost and the minimal cost of a refinement, and hence this forms the minimal cost of this refinement sequence. And then if we capture the minimal cost of all possible refinement sequences that get to the stable refinement we were looking for, then that is a lower bound for partition refinement algorithms. So the only thing we require for these refinements is that they are strict in the sense that we make some progress, and also that if states are splitted in a block, then there is a reason that the states are splitted. If you can't observe that the states are different, then you should not be able to split the states. Then we don't call it a partition refinement algorithm anymore. So now that we've captured the partition refinement algorithms, we can introduce the LTS, the bisplitter label transition system BK, that exhibits a growing set of action labels. So first, I will do this by example. So first we will start with B2, which is a label transition system that consists of 4 states, and they are labeled with bit strings. So 0, 0, 0, 1, 1, 0, and 1, 1, the bit numbering of 0 to 4. And the line represents the initial partitioning. So now if we want to do partition refinement on this LTS, we have 2 choices. We can either split the block on the left side, or we can split the block on the right side. However, there's only one way to split it, namely we have 0, 1 that reaches the right side with an A, and the 0, 0 stays in the left block with an A, so it does not reach the right hand side with an A, and hence we split these blocks, and we have to move 1 state. On the right side, the same thing happens, namely 1, 1 is able to reach the left side, whereas 1, 0 is only able to reach the right side. Hence we split this, and we also have to move 1 state. So in order to partition this LTS, we have the cost 2, which is exactly the half of the number of states. Now in order to obtain B3 from B2, we start with the previous bisplitter B2, and we take a 0 copy and a 1 copy, where we prepend the bit strings with a 0 and a 1. These 2 LTSs, which are now disjunct, form the initial partitionings, and then we add a fresh action label, B in this case, for which if the second bit in a state is a 0, so that's 0, 0, 0, 0, 0, 1, and 1, 0, 0, and 1, 0, 1, we add a self loop with this fresh action label B, and on the other one, where the second bit is a 1, the remaining states, we add the fresh label to the first state of the other block, like this. It gets a little bit complicated, but this is what happens. And now, if we want to do partition refinement on this LTS, we see that the letter A, which stems from the previous bisplitter B2, does not observe any splits because they all stay in the same block. So we can only split on the letter B, which arrives, which goes to the other block, and this means that we split either we split the states that go to the other side, and the states that maintain in the same block. So we split exactly half of the states, which means we have to move 2 states. We do the same on the right side, and there also we have the states that reach the other block with a B, and the states that maintain in the same block with a B. So this also has a refinement cost of 2. So in the total, these 2 splits will cost exactly half of the states, 4, which is 4. So now we have obtained this partition on this LTS, and we can see that this newly added fresh label B does not witness any split anymore, because in the first block the B only has self loops, so this does never witness a split. In the second block, the B transitions go to the same state, so it can also never witness a split. In the third block, the same happens as in the first block, namely we have only self loops, and in the third block they also go to the same state, so this does not perform any split. So we can kind of ignore the newly added label, and we can only look at the A labels, and then we found out that this is actually just 2 copies of the first bisplitter B2, which we kind of have to split through the middle, which also cost 1 for each block. So it's again cost 4, which is exactly half of the states. So this is how we've created B3, and we can repeat this process. So we copy all of these states, add a 0 copy and add a 1 copy, add a fresh label, and connecting these blocks such that it has to split exactly through the middle as a first split, costing half of the states. And this way you repeatedly move states, the half of the states in every step, and you have a logarithmic amount of steps. So we have a family of LTSs, BK, in which we have exponential amount of states, n is 2 to the power of k. We have a logarithmic amount of action labels, namely k minus 1. And we have 2 to the power of k times k minus 1, because it is deterministic. Every state has an outgoing transition for every action label, transitions. And in the way that it splits, namely that you have to move exactly half of every state, and for every time we made this bk for the k, we get that the refinement cost of this bk is n log n, which is in the order of the transitions, but in the order n log n of the states. So now that we've shown how we can make a LTS bk with a growing set of action labels that exhibits an omega n log n lower bound for partition refinement algorithms, we show how we can modify this LTS in order to obtain the LTS CK. The CK has only 2 action labels and is deterministic, and it also exhibits the lower bound that is exactly the runtime complexity of page-Tarion algorithm, namely the omega n plus n log n. So we only use 2 action labels A and B, and we want to simulate the behavior of the LTS BK, the bisplitter, and we do this by, for every state we add a binary tree, and on the leaves of this binary tree we simulate the behavior of a transition of BK. So this is an example of one tree for one state in the LTS C6. So so this is a state with a bit string of length 6, and we add all these auxiliary states to keep in memory. So a word of length 3 now forms one transition in the LTS B6. And then on the first leaf we have the first transition, on the second leaf we have the second transition, and this way we will fill up all these leaves with transitions of the LTS B6. In this way, when we want to split, where we want to apply partition refinement, we have the same partition refinement pattern, only we have these intermediate steps where we have to split through the leaf, and this information persists to the upper state, which is connected with leaves of other trees in the system. This way we have the same splitting pattern, but we did add a lot of auxiliary states. So for every state we have a lot of states we added to keep this information. And in order to leverage all this information, we replace every state with a stake, what we call stake, which is basically a lot of useless extra states which follow the behavior of the state of one level lower. So every state is now a sequence of states which directly follow each other, and on the end of this stake sequence of states there is the tree gadget we mentioned, which simulates the behavior of B, the bisplitter BK, and the outgoing transition of the tree gadget are connected to the top of the top of the stakes, which will then again be a stake and go through a tree gadget which simulates the behavior of BK. So in this example of B3 we have the state 1, 0, 1, which has 2 outgoing transitions with 2 different labels. One is going to 1, 1, 0 and one is going to 1, 0, 1. However, in the new transition system CK we have this long sequence of 8 states, where the bottom tree has exactly these 2 outgoing transitions. But if there were more outgoing transitions, then this binary tree would have a higher depth in order to simulate all those distinct outgoing transitions. If we combine these 2 gadgets, we obtain the LTS CK, and in this picture you see the example of the LTS C3, where we omitted some transitions to improve readability. So for this one state 1, 0, 1, you can see all the transitions. So on the bottom we have the outgoing transition of the tree gadget. They connect to the top where they, on the state where they would go to in B3. So the trees imitates the transitions from BK. The stakes are there to leverage the number of states and to achieve the lower bound. And the initial partition is leveraged from BK, and every state on different level are in a different partition initially, to simplify the proof. So this LTS still exhibits the behavior that we have to split exactly in half at the block in halves. The only difference is that it follows a long path before it reaches a previous bisplitter, and we get this recursive behavior. So now we've shown how these gadgets help to obtain the LTS CK, which have our main theorem, namely that the lower bound for partition refinement algorithms is the m plus n log n. But there is one way that is used to calculate strong biosimulations on a one-letter alphabet, which is due to Robert Page, Robert Tyen, and Robert Bonich in 1985, which uses the structural properties of single-letter functional LTSs. So they have found some structural properties that can be helpful to calculate, and then afterwards derive the strong biosimulation, the biosimilarity classes for every state. And actually this algorithm is not captured by a partition refinement algorithm, so we can't observe a run of the algorithm as a sequence of partitions. So the question would be, can we apply these IDs to help partition refinement algorithms become faster? Can we first calculate these structural properties and then apply partition refinement? And the answer is no. We've shown this with the help of an oracle, that if we have this structural information about the LTSs on multiple letters, then even then partition refinement will be in omega n plus n log n for partition refinement algorithms. Thanks for watching this presentation. For further details, I refer you to the paper.
Okay, good. Thanks, Jan. And I think we still have 2 minutes, so we can pick maybe a very quick question. Has anybody? Okay. Yeah, mind? Rob, you are raising your hand.
Yeah.
Yeah, can you speak? Yeah.
Yeah. I will ask a question. I was thinking, Rob van Glabik, by the way. We have a lower bound, and you now show you cannot be, you have a normal complexity measure, you show you cannot do any better if it's partition refinement algorithm.
Yeah.
But in principle, there can be arbitrary many algorithms that are not partition algorithmic refinements that do much better. And my gut feeling is, well, there aren't any really. I want to know if you share that gut feeling, but more importantly, do you have any formal way to put a bound to that? There must be some kind of lower bound for general algorithms that one can calculate.
Thanks for the question. It's a very interesting question. I share the same feeling. So I would say any reasonable way to attack this problem, to make an algorithm would involve some kind of partition refinement way, or at least if you want to go for efficiency. But actually, in the literature there are not many very useful strong lower bounds for generic algorithms. Even the lower bounds known for sorting list, for example, take some kind of assumption on what kind of algorithms we can use. So actually, if you know something about this, I would be very interested. But it seems very hard to translate this to a generic lower bound.
Okay, thanks.
Yeah. Other questions? Actually, I have one very quick question, because it seems that your result works for deterministic LTS, right? Mm-hmm. If the system is non-deterministic, can the result still hold?
So because it's a lower bound result, when the model is weaker, that actually implies that. So if we could solve non-deterministic LTSs, then we could also solve the deterministic LTSs. So we show that partition refinement is this lower bound holds for partition refinement even in the case of deterministic LTSs, so it automatically also applies for non-deterministic. And actually, the construction was non-deterministic at first, and then we applied these gadgets to make it deterministic.
Okay, good. Thank you.
Yep. Thank you.
So we're going to move to the third talk. Okay. Anyway, we thank the speaker again. Now we move to the last talk of this session. The talk will be given by Wei-Yu Wang on enabling preserving biosimulation equivalence. So please, Wei-Yu.
Hi there, my name is Wei-Yu Wang. Today I'm going to introduce you to enabling preserving biosimulation equivalence, a bisimilarity that preserves drowsiness. We first talk about drowsiness. Suppose Alice is in a coffee shop and wants to drink as much coffee as possible. Bob is doing the same in another coffee shop. We use a transition system to model this scenario. If Alice gets a cup of coffee, then transition A is executed. For Bob, we have transition B. We assume that the baristas will never stop working and there are no other customers. Then, which path models the possible behavior of Alice and Bob? A finite path? Of course not. An infinite path where either A or B occurs only finite times? Well, Alice and Bob are served by different baristas, so their actions should be independent of each other. We should expect that both transitions will occur infinitely many times. This is the case when we assume weak fairness. It says if an action is always enabled, it will be taken eventually. If a path models the correct behavior of the system, we say it's a complete path. The fairness assumption here is called a completeness criterion. It is a selection of the complete path. When we verify Leibniz properties, we always need such a criterion, and will only verify properties on the selected path. Otherwise, in the worst case, an empty path will be allowed. Thus, no interesting Leibniz properties can hold. Now we have Alice and Kathleen in the same coffee shop. Transition C is there for Kathleen. There is only one barista and he can serve only one person at a time. It should be possible that he forgets Kathleen's order and serves Alice only. Thus, it suffices to have a transition A or C occurring infinitely many times. Let's add Bob back. Again, Bob is served by a different barista, so he will get as much coffee as he wants. Which means transition B should also occur infinitely many times. Fairness is too strong here, so we turn to drowsiness. It says that once a set of parallel components enable a transition, at least one of these components will eventually partake in a transition. Here, the two baristas can be viewed as the components. It should be fine as long as they repeatedly serve coffee. Generally speaking, fairness tells us that two independent events should not block each other, and that if we repeatedly make a choice, all the options of the choice will eventually be selected. Here, the barista is making such a choice between Alice and Kathleen. Drowsiness agrees with the first statement, but allows us to make the same choice every time. To this extent, drowsiness is more realistic in some situations. However, there is a problem. On the screen, we have two systems. The system on the left models Alice and Bob in different coffee shops, while the one on the right models them in the same coffee shop. The two transition systems are strongly bisimilar, but the A loop on the left-hand side is unjust, while the A loop on the right-hand side is just. This is because the relationship between transitions is not considered by the labeled transition systems. For example, on the left-hand side, the execution of transition A will not affect transition B. We use this notation to indicate this fact. We call it the concurrency relation. For the system on the right, the execution of A will interfere with B. Moreover, if a transition T is not affected by another transition U, then afterwards, a successor of T will still be available. In the system on the left, the successor of B after A is B itself. We use the successor relation to denote this fact. We read this notation as V is the successor of T after U. Here we require that T and U must share the same source, and V must be enabled at the target state of U. The concurrency relation can then be derived from the successor relation. We say T is not affected by U, if and only if, after U, T has a successor. We add the successor relation to labeled transition system and call it LTSS, the labeled transition system with successors. Okay, we have filled in the missing information. Let's formalize justness. This old definition of justness is based on the concept of parallel components. We now rewrite it to, once a transition is enabled, this transition or its successors will eventually be interfered with. Look at the system on the right-hand side. We have T1 as the successor of T0. If T1 is again not affected by U1, then there will be its successor T2. This continues and gives us a successor chain from T0 to Tk along the path. To make the path just, we need some Uk in the path that interferes with the current successor Tk. Thus, the successor chain is broken. From this example, we can summarize justness as no infinite successor chain along the path. Now it's time to introduce enabling preserving biosimulation. We call it EP biosimulation. A lot of biosimulations, including strong biosimulation, is a binary relation between states. However, it does not work in our case. Suppose we have a system where T and U will not interfere with each other. Assuming that the biosimulation is reflexive and the two transitions share the same label, without any relation between transitions, by making transitions that share the same label, an unjust path could be related to a just path. To solve this problem, for each pair of related states, we further assign a relation between transitions. We have also tried the union of a state relation and a transition relation, but it does not work. We ended up with a bisimilarity that is not transitive. So, an element in EP biosimulation is a triple. The transition relation R only rates the transitions enabled at the state we are looking at. To some extent, we can say the triple rates the structures. Each one is composed of a state and its outgoing transitions. Just like strong biosimulation, if we have a transition on one side, then there must be a related one on the other side. And the other way around. Of course, the related transitions must share the same label, and their targets should also be related. What we have now is just a triple version of strong Biosimulation. To preserve justness, we further require that the successors of the related transitions are also related. Look at the system on the right. Suppose T0 and U0 are related. If T1 is the successor of T0, then it must be related to some U1, which is the successor of U0. In other words, the relation between transitions is inherited by their successors. This requirement is symmetric, and we are done. If we have two paths related by an EP Biosimulation, and one of them is unjust, then along that path, we must be able to find an infinite successor chain. With the requirements 4a and 4b, we will be able to find a corresponding successor chain along the other path. So, if one path is unjust, then the other must also be unjust. Therefore, justness is preserved. EP bisimilarity is then defined using this EP bisimulation. In our paper, we have proved that the union of any collection of EP bisimulations is itself an EP bisimulation. EP bisimilarity preserves justness, and is an equivalence relation. The choice and the parallel composition operators are associative and commutative up to this equivalence relation. Moreover, EP bisimilarity is a congruence for all standard process algebra operators. For the last two properties, in the paper we use an extension of CCS with broadcast communication and signal emissions. We call it Abcde. With signal emissions, we can have transitions like this. Emitting the signal will not change the state of the process. Thus, it will not affect other transitions. But if we perform a transition and change the state, then the signal emission is no longer available. By the way, as shown on the screen, a transition in Abcde is in fact a proof tree. In this example, T will be affected by U, but U will not be interfered with by T. In pure CCS, the concurrency relation is symmetric, but it is not the case with our extensions. Finally, I would like to show you the successor relation in Abcde. Suppose we have a parallel composition P parallel to Q, as on the left. Let T be the transition stems from P, and U be the one stems from Q. After the execution of U, we can still do a transition V, which stems from P. The only difference between T and V is that Q becomes Q prime. We say V is the successor of T after U. This is the end of my talk. Thank you for your attention.
Okay, thank you for the talk. I think we now have a lot of time for questions. So, yeah, I see someone is raising hand. So, yeah, please can see.
Okay. I can ask a question. Thank you for promoting me, and I encourage the other to raise their hands. So my question was about the why do you define this notion of LTSS to be able to encode the justness? Cannot you use one of the many models like event structure or transition system with independence? Cannot you just express justness in one of the existing models? And so you can compare your AP by simulation with the many ones that exist there.
The short answer will be yes. We have also looked into other candidates of the models. For example, we have a model called LTSC, where we only have the concurrency relation. And we also have LTSCS, where the concurrency relation and successors are both there. We have also looked into LTS with the notion of components. So there we have two functions which give us the necessary components, and the components will be affected by taking some transition. But for the other models, I'm not so sure. So maybe Rob or Peter can give the more answers. But for now, we only looked into those models, and I strongly believe that only those information can capture the notion of justness. It is possible that later we can create some canonical mapping from other models to our LTSS, but we believe that the successor relation is exactly what we need.
If I may ask, add a few words to that. This is Rob van Glabbeek for the people who do not see me. We have ideas on how to translate many other models of concurrency into LTSSs. LTSS is a very, very general model. So I think we can translate patrinets, event structures, higher dimensional automata, or transition systems with independence into LTSSs, and thereby the biosimulation that we have for this model can also be applied to these other models. So in some sense, it's at least as general as if we would work in those models. But in some way, it's more general because the process algebra that we used featured broadcasts and signals, and we chose those exactly because they are features that cannot be modeled in standard patrinets or in standard event structures. You would have to wiggle around with these models to make room to model broadcast. And this has to do with the asymmetric concurrency relation. In the patrinet, the concurrency relation is naturally symmetric. So in some sense, our model allows us to extend it to these language features that we would not be able to handle with some of the more classical concurrency models.
So do you have an application or a real protocol where you can model with this kind of EP biosimulation instead of the strong biosimulation? Because you have shown some theoretical results, I won't see. I mean, in practical, this is really very useful or not?
Yes, this is our next step. And one of our next steps is to prove that EP bisimilarity is also a consequence with respect to recursion. And then out of that, we will use it to try to do some formal verification of some protocols, for example, some logs.
Yeah, we are thinking of logs or a garbage collector as very good examples where we think that this will be the right framework. This is yet to be substantiated.
Yeah. Okay, we have one question in the chat window. Jan Martens has a question. So how efficient is it to calculate EP biosimulation? What's the efficiency?
I think the short answer is we don't know. Well, yeah. Maybe you know, I don't.
We do not know. It's decidable in a very clear way, but that's as far as I dare to go. It might be that it's as polynomial as a normal biosimulation based on the fact that you just look one transition ahead, but we have not tried to generalize normal partition refinement algorithms to this new setting. That also might be a very cool topic for future work. We looked at some other relations that might also be justice preserving, for which we thought this is not even decidable or very high complexity. And this was one of the design criteria to come up with this relation, but still we don't know.
Yeah. Someone is raising a hand. So who is raising a hand, please?
Yeah, it's me, Stefan Milius. I have a follow-up question on this. So is there anything known about whether these LTSSs are coalgebras? Because if they are, then these generic partition refinement algorithms that we have are immediately applicable. I mean, modulo checking some properties of the functor, if they are. But, well, I couldn't see this quickly. So this could be something to look at. But maybe I'm off with this.
I find it a very intriguing question, and I very much hope they can be cast into this framework. But currently, I lack, even after understanding what you did in your talk, I lack the creativity to see what we use instead of distributions or power sets of other standard tools to make it into a coalgebra. But it would be wonderful if that gave us a partition refinement algorithm.
Mm-hmm. Actually, since we still have 8 minutes, so we can even ask questions about the previous 2 talks as well. Actually, I have one for the talk of Torsten. So you construct this kind of certificate for this kind of bisimilarity. So can you do that if you have the transition system which is probabilistic? If you take probabilistic LTF, can you still construct similar kind of certificates or not?
Yeah, so this algorithm supports both the probabilistic and the non-deterministic branching. So, I mean, in the certificate that's constructed in the end, this will feature both probabilistic modalities and the usual modalities, and it will be kind of a mixed formula, but in principle it works. Yes.
Okay.
Yes. So we have it, if you mix multiple types, we have the actual partition refinement algorithm formulated quite precisely, but for actually it's still a bit work to do to get it everything formal for the certificate construction also.
Yeah.
But in principle it works. Yeah.
Okay, I have one more question. Actually, for all the 3 talks, because all the talks talk about strong bisimilarity. So how about weak bisimilarity?
Well, we claim that strong bisimulation is too strong, so then it's too weak. Sorry, so then weak bisimulation is definitely too weak for our purpose.
Okay.
Yes, but we generalized strong biosimulation to strong enabling preserving biosimulation, thereby making it even stronger. Obviously, in order to apply this stuff to, say, model the correctness of a garbage collector, we would have to use a weak version of enabling preserving biosimulation.
Okay. Yeah.
And I have some idea that this can be defined by logically combining the ideas between the enabling preserving biosimulation and the weak biosimulation, but again, this yet has to be done.
Yeah,
so I think it's always a good plan to do something in the easiest and strongest case first, especially since it's a difficult thing. And then once you have that down, go to the weak case.
Yes.
Yeah, so for our result, I think maybe it's interesting to note that because there's a negative result and we go top down, that our result automatically implies that for branching and weak bisimulation, these lower bounds also hold for all weaker equivalences.
Yes, and so for the second talk, for the coalgebraic partition refinement, I can say, so what the coalgebraic partition refinement is actually about is a general equivalence called behavioral equivalence for coalgebras. And this just so happens to instantiate to strong bisimulations if your coalgebras are transition systems, and it's probabilistic bisimulation if you have Markov chains. It's language equivalence if you have automata. So behavioral equivalence for coalgebras can be different things. but definitely weak biosimulation of transition systems, that's out of scope currently. And yeah, one would need some new ideas to extend the whole framework of this generic partition refinement to that. And also other kinds of biosimulations or trace equivalence of transition systems and so on.
Okay. Good. Any other questions from the audience?
If I just can come back to what Jan just said about your framework being applicable to weak versions of biosimulations, I find it a bit hard to believe that just works for any weakening, because it depends how you define the relation in biosimulation style. If you take the universal relation, it's a weakening, but it has a very easy decision algorithm. So there must be something in your lower bound that depends on the nature of what equivalence you consider, right?
Yeah, I think that's a good point. But so I was referring to the refining relations, I should probably say, because if the relation you define like branching biosimulation and weak biosimulation would imply strong biosimulation on transition system without silent steps, then then this lower bound would remain, but not on every generic equivalence, of course.
Yeah,
if that's more more clear.
Yes.
Other questions?
If I may.
Okay. So we have very fruitful discussion about biosimulation in this session, and we should thank all the speakers. And I think now we end this session. Okay, thank you all. Bye-bye.
Thank you too, Yuxin.
Thanks.
Yeah.
Bye-bye.
Thanks.
Thank you.
Bye.